This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Geometry, because usually when you've got a process or a standard cell library, usually there's multiple inverters in there. It's not just one, right? And they've got various sizes and different drive strengths. But suppose here we're talking about the minimum size inverter, or the inverter made with minimum size transistors. What we're able to do, and even if it was the larger ones, it's still applicable. But what you're able to do is to build these inverters. What you can actually then say is, well, what is my delay? Or you use what we've learned so far, which is that the delay is the gate complexity times the electrical effort plus the parasitic delay. And what you're able to do is, for an inverter, I can actually work out what the delay through this one inverter is in terms of logical and parasitic delay, and it's 2 units. It's standardized relative to itself, so therefore you would expect it to be a nice round number. And then what we're saying is, how long does it take, what is the total delay through this, if we had n of these inverters, we know that the delay from a 1 to 0 transition is d. If we're going from a 0 to 1 transition, it's 2d. And if we've got 2 stages, the delay would be n times d times 2. We know d is equal to 2, so it's 4n. So the period would be 1 on 4n times t. Right, where t is the propagation delay through that, through any one inverter. Right, so therefore that gives you an indication of what you expect, how fast you would expect that oscillator to oscillate, or what its period of oscillation or frequency of oscillation is going to be. Right, so and I gave you a little bit of background, not relevant to the exam, not relevant to this course, but when you're employed and you're actually building chips, I also pointed out that one of the tricks that people usually do is put ring oscillators on the chip, just all over the place, so therefore you can actually tell what skew you've actually got on your actual process. Are you on a fast corner, or you're on a nominal corner? Because as we said, as you're building these chips, depending on where you are on that wafer, you get more or less doping, and it also affects the performance. Right, so this is one of the cheap and nasty tricks that people use in order to work out what are the characteristics of that particular chip, right? Because even though you're building millions of chips or hundreds, maybe thousands off the wafer, they're not all exactly the same, right? And this gives you the ability to be able to understand and quantify this process variation. Now, I followed up with talking about, well, this linear delay model. It's quite a nice, easy, intuitive way to start calculating what we expect the delay and the performance of a particular process is going to be. And of course, if we had a particular circuit, what can we, how can we estimate the delay and the path delays and the rest? Now, what I wanted to highlight here was, or I did highlight was, hey, there are some limitations to this model. The linear delay model is great. It provides a lot of intuition. It gives you some great insights, but it has some limitations, right? And there I went through and described what the limitations were. And essentially there I said, well, one of the fundamental assumptions in this model is that you've got a very sharp edge. Right, so therefore your input changes, the derivative of the input at the transition point is almost infinity. It's goes almost straight vertically up. And of course, as this changes, as you get more and more delay, and that could be due to slewing of your previous stage. Your previous stage might be trying to drive a large gate that's following it and doesn't have enough current drive. What happens is essentially that gradient decreases, going from infinite to some finite value, hopefully not 0, but it's some largish value. And essentially what happens there is, if that occurs, there are some issues that you've got to be aware of, and this linear delay model begins to break down. And depending on the circumstances, you can be a non-insignificant percentage off in your estimate. Then we talked about some of the other limitations. We talked about input arrival times, and essentially what it does assume is that all the inputs arrive at the same time, or the other way that they represent this or the other assumption is you can either say all inputs have to arrive at once, or only one input can change at a time, right? But you know, that's a serious limitation. But notwithstanding that, it's the linear delay model is still very, very, very useful. But it's just knowing when you've got some problems, and when you've got to look out. And then we started to talk about velocity saturation, and of course we ended off by talking about voltage dependence. And there, what we were describing or talking about was, hey, we know, and we're going to talk a lot more about power and power dissipation in high-speed electronics, because other than delay, one of the other things that's critically important is power, and how do you dissipate this power, and how do you manage this power. We're going to start talking about that on Friday. But one of the issues that I wanted to highlight was essentially that that once you change the supply voltage, your propagation delay has a non-linear relationship with your supply voltage, right? So therefore, what you would normally do is, in your standard cell library, or if you were doing a layout and you're doing a parasitic extraction as part of your design, one of the things that you would do is you would choose a supply voltage and then work out what you would expect the propagation delay for an inverter with that supply voltage to be, right? Because you can't just say, I'm 3/4 of a volt, so therefore, my propagation delay is going to be 3/4 or something. It's got a non-linear relationship. Now, why did we decrease the voltage? We said we could decrease the voltage, and why did we want to maybe decrease the voltage? In our logic? Yeah. Sorry? To lower power consumption. And why voltage, not frequency? That's right. It was V squared. Remember, it was half CF V squared. Perfect. All right. Excellent. So now let's start by looking at these systems or collection of these circuits or gates, and look at logic paths and start working out do a little bit more definition, and also look at some more examples. Okay, so in this particular case, all I'm drawing here is a very simple logic function where I've got an inverter, an XOR, NOR, NAND inverter, and then some kind of load, right? And what's important here, and I emphasize, just so if you see it again under different circumstances, when you see 20, what I'm saying here is that's the capacitance there is 20, equivalent to 20 inverter units of capacitance, right? That's what that 20 means. So it's not 20 picofarads, it's 20 equivalent of 20 inverter capacitance units. Okay. Why do I do it that way? I do it that way because then it allows you to not need to worry about units and conversions and the like when you're doing all your calculations. Now, we have defined logical effort. Okay, so I mean, other than having the values up on there, can someone tell me what's the logical effort for a inverter? I've got the number there, so it's a bit dumb question, but one. Okay, and so how would you find this? Like, for example, if I gave you this in a test or in an exam or something, how would you find these values? So you'd find G, whatever. Where would you go find these values? A table, okay, right. So you need to look up in the table and find what these values were. And what we've done in the previous notes, what we've shown is, for example, an inverter has a gate complexity of 1 and NOR 5/3 if it's got 2 inputs, and an AND 4/3, an inverter again 1, and this is just a capacitor. It has got no no logical effort. It's just got, you know, what do you call it? That's just a capacitor. All right, so we defined electrical effort. So can anyone remind me what was, other than saying X on 10, how do we define electrical effort? Output capacitance over input capacitance, right? And then the other thing that's important, just to emphasize and just to make sure that we're all on the same page and we've got consistent terminology, if I write X here, that's usually the size of the device, right? So therefore, here what I'm saying is Y on X, you know, Z on Y, 20 on Z, and that's the electrical effort. Does that make sense? So it's electrical effort is C out on C in. So therefore, C in Z, C out's 20. So the electrical effort here is 20 on Z. Okay. Now, what we're going to do here is, this is actually a definition. So I'll put those little symbols there so you're all happy and don't, you sort of like say, where's all this coming from? So there's this, oh, and I even had it here. Geez, I didn't even see it. Okay. All right. So what I want to define is something called the path logical effort. And essentially, when I'm talking about path logical effort or path efforts, what I'm saying is, if I had this path, like path 1, what is its... Okay. If I had this whole sequence of circuits or sequence of gates or connection of gates, what is the overall, you know, logical effort, electrical effort, or the total path effort? What I'm referring to is that whole connection of gates. And what we'll do now is work out, how do we work out what that effort is, what these we'll define these quantities and then work out how we determine these quantities for these connections. And the other thing that's important here is, here I'm drawing it linearly. What we'll do is, later on we'll also talk about branching, where you might actually have, you know, this inverter, but you might have another, at the output here, you might have another circuit connected up to it, right? So you might have a branch, right? But what I would usually do, or, you know, when we're talking about a particular path, we're talking about from input to output, right? For that particular output, right? So if I had another circuit here, the path, what I'm talking about is that path. What's the total effort from here to this point? All right, when I'm drawing P1 here. So from here to here. All right. Okay, so we're going to define the path logical effort, and we'll call that capital G. And what you find, or what it turns out to be, is that it's essentially equal, or you can say it's defined as the product of all the logical efforts of all the components in this circuit. So, if you were looking at this particular circuit, can anyone tell me what they think the path logical effort would be? Sorry? Yes. Everyone agree? All right. No, I'm just trying to make. I mean, of course you agree. I know you can do the maths, but what I'm saying is, do I need to explain it any further? Okay, good. So we're all good. Now, the path electrical effort is essentially the capacitance of the output to the capacitance of the input, right? So it's the output of the path to the input of the path, right? And that's distinct to when we were looking at the electrical effort for a gate, right? For a gate, we were looking at each gate independently. Whereas here, what we're looking at is the path electrical output is the input to the ratio of the output capacitance to the input capacitance. Now, you can actually convince yourself that that's, of course, going to be the case, because if you looked at, other than this definition, if you looked at this and you worked out the product, you'd have x on 10 times y on x. The x cancels out. So you got y on 10, z on y times y on 10 is z on 10, right? Because the y's cancel out. The z's cancel out, so you'll have 20 on 10, right? So therefore, it's essentially the same. It's the product of HI's, but what you find is they all cancel out, and it turns out to be equivalent to the output value, the capacitance of the output of the path to the capacitance of the input. Okay. Now let's talk a little bit about path effort. Okay. And the path effort is essentially the product of the stage efforts, right? And this, of course, I'm assuming here that there's no branching. And what we'll do is we'll work out what happens when there is branching. So if there's no branching, just re-emphasize this, it's the product of all the FIs, or the logical of the path, or the effort for each of these elements, which is the products of GI, HI, right? And what you can do is, if you know that the product of products can be rewritten as the product of these two products. And what we've got is this path effort is capital G times H. Right. Okay. The notes should be up, so I made sure that before I came to the lecture I put them up, so you should have the notes. Okay. Now, what I'm going to talk about next is branching effort, right? And so far, what I've done is said, well, let's look at this circuit, and I'll refer to it as it's a linear circuit. It has no branches. Well, what do we do if there is a branch? Okay, and what we find is we define this concept of branching effort, and essentially the branching effort is defined to be the capacitance on the path plus the capacitance off the path on the ratio of the capacitance on the path. So let's do a little example here. Suppose we had this inverter. Jeez, I'm sorry. Yep, one input, not two. And I asked you to work out what the branching effort is for this particular structure or circuit. And essentially what I'm saying is, if I'm looking at, I want you to work out the branching effort for this, or the path effort for this. The branch effort is essentially whatever's on the path, which is 15, and we only look at, and at this point we're only looking at the input. Don't add the 90 here, right? It's only what, you know, the input to that gate. So the input to this gate is 15, so that's the on path. The off path is 15, and divided by 15. So therefore the branching effort is 2. Let me see if I got a piece of paper and I can give another example. I won't write on the back of your exams because then they'll photocopy it and then you'll have... Okay, so what happened... Okay, quick question. 7, 12, 27. What would be the branching effort here? Ah, good point. You can't read minds? I meant this one. Okay. What would be the branching effort here? Yes. All right, good. Yeah, so don't include this. This is on the path. This is not off. This is off path. On path, so it's 19 on 12. Excellent. All right, good, good. And if you've got multiple branches, so here what I'm saying is if you've got multiple branches, so let's think of the following situation. So the branching effort, if you've got multiple branches, is the product of the branching effort. The products of a branching effort. So if you had the following situation, essentially all I'm saying is, suppose you had the following situation. And for argument's sake, say, just to make it all easy, 15. All right. What's going to be, what would we expect the total branching effort for this path to be? 2 or 4? 4. Because it's 2 here, right? Because there's one branch here and it's 2. Sorry. Yeah. So, yeah, 2 here and then there's another 2 here, right? So it's the product. Good, good. All right, let me put that away so you don't get myself. All right. Okay. So the point here that I'm trying to make is if you've got, sorry, have I moved it up too high? I've got some people looking, have got horror on their faces. Is it okay? Have I made a mistake or have I moved it too high or all good? All good. All right. Okay. Good. Good. So the point I'm trying to make here is that if we've got branching, what we do is that the total path effort is the path logical effort, which was the product of all the individual logical efforts for each of the gates. The total path branching effort, right, which was as we worked out, is the product of all the BIs. And the path electrical effort, which is, what was it? It's a product of all the HIs, which is the same as... All right, let me go back to this one. Just if I was just showing you this and I said, you're not allowed to have a calculator or anything, what's the H for this circuit? For this path? What's capital H? Yeah. All right, you can sit there and try to work it all out. Go 12 on 5 times 27 on 12, and then cancel out. Or the simplest way of looking at it is capacitance of the output, capacitance on the capacitance of the input. Done. All right. Good. Now, what we're going to do next? I'm going to hide this. Is to work out the delay of a circuit. And what we're saying is the total delay is equal to the sum of the delays, as you would expect, right? Which is equal to this df plus the parasitic delay. Total logical delay, logical path delay, sorry, and the total parasitic delay. Now the parasitic delay is just you sum up all the parasitic elements. Here you work out the sum of all the GIs, HIs, and sum them up in order to get the F. Right? So that gives you, this is the total delay in terms of what? Because it's, no, in terms of one inverter delay. Okay? All right, so let's have a bit of fun. I mean, this is why I don't like putting the lecture notes up there, because then I can't do this trick, right? I can't be like, all right, give me some interaction so I know what you've learned and have I explained it sufficiently well. Okay, suppose I've got this circuit, right? Okay, can people go through and just tell me what's the logical effort for an inverter? Perfect. The NOR. Yep. NAND. Okay, and and if you have inverters, 1. Okay, perfect. All right. Now, can someone tell me, right? Now, what I'm going to do is I'm going to actually work out the HIs for each element rather than the path HIs, right? What the electrical effort is. What's the electrical effort H1? Yep. All right. And H2? All right. H3? X. All right. And H4? 20 on Z. Perfect. All right. What's the parasitic delay of each of these elements? All you're doing is just looking at the table. All you're supposed to be doing is looking at the table, right? Unfortunately, I've given you the lecture notes. Now you're just reading the lecture notes. But the problem there is, by doing that, I don't know that you know how to go back and look at the table. I assume you do, but it's okay. So what we do is we look at the table and we look at the parasitic delays, and we see that inverters 1 and the NOR and AND are 2. Okay. So the delay, as we discussed, is D equals Fi plus Pi. All right, and essentially all I'm doing here is it's working out. I should put that write it like that, otherwise you might get confused. These are the parasitic delays, and essentially what I've done is the logic delay times H1. So G1 times H1. G2 times H2, G3 times H3, times H3, yep. All right. So therefore, plus H4 on, okay. Yep, plus the inverter there, okay. So let me do this. Okay, and these are the H's and the, so let me just do this for you, which is G1 times H1, G2 times H2, G3 times H3, G4 times H4. Okay, just making it a little bit more clear for you, and you can work that out. Now you can also work out your F, which is GBH, right? So therefore G is the product of all the, how do you call it, all the gate complexities, branching. What's the branching value? It's 1. Why is it 1?
No branches.
No branches, perfect. And then H, is the product of H's, and as I said, it's just the output capacitance on the input capacitance. So therefore, the total logical effort is 40 on 9 units. So this is the delay, this is capital F. I'm working out something else at the moment. And what we're saying here is, and what's interesting is that the total F is independent of gate sizes, right, at the moment. So what we've done is we've got a way of being able to work out what our logical effort is independent of gate sizes, right? And if we made the inverters and everything larger, then we know that what we need to scale up by. Okay, good. All right. Now, some interesting stuff, or more interesting stuff. Suppose you wanted to work out the minimum. So you had a complex circuit, right? And you had a sequence of gates, right? And then the question you asked yourselves was, hey, I want to make this the fastest I can, right? How would you do it? Well, you can start playing with each of the components and trying to do an optimization. But generally, what you can prove for yourselves is that the min of this, I mean, you can't optimize the parasitic delays, right? Because you need to have, the parasitic delays are going to be the parasitic delays, okay? But you can optimize your, how do you call it, your logical effort. And so therefore you ask yourself, how do I size each of these gates so that I get the minimum delay, right? So therefore that's the question you're asking yourself. How should I've got a logical function, and I've looked at that logical function, and I'm not going to put any XORs in there because I know that XORs are pretty bad. But what I've got is I've got the function. The next thing is how am I going to scale this? How am I going to size each of these components such that I have the minimum delay? That's always an important question, right? Okay, because you want to remember, it's high-speed electronics. Everything's about making it high speed, right? So the question is, how do we make that delay as small as possible? And essentially what we're saying is, how do we size? Essentially, the only thing that we've got available to us now is we've chosen our process. Very likely, our company or our boss or whoever said, you're using 65 nanometer or using 28 nanometer, right? You've got no choice, right? So you've got to use a 28 nanometer or a 7 nanometer or whatever process. So you've got no choice. You want to implement a particular logic function, you've got no choice, right? If you're trying to build an arithmetic logic unit, you can't change the logic, right? You can implement the architecture a little bit differently, but let's assume that you've chosen the optimal architecture. Now, the only thing that you've got available to you is size these gates so that you get the minimum delay, so therefore you can get the highest performance, right? So the question is, if you're trying to work out the minimum delay, where what you can actually show is that minimum delay occurs when all of the gates have equal effort. All right. Now you can go through and you can try to solve this optimization problem. So this is the optimization problem that you will need to solve. A lot of you are probably doing signal processing or advanced signal processing or optimization or whatever. So this will be a very fun exercise for all of you that love doing that kind of crap. Apologies, I didn't mean that, sorry. But essentially what you do is you can actually prove for yourselves that minimum occurs when each of the gates has the same path effort. So what that says is GIHI, right, is going to be equal to 1 on n, f to the power of 1 on n, right? So now let's look at this a little bit more carefully. So if we've got n stages, all we're saying is we're going to make each stage approximately equal in path effort. That's the way. That's the only way that we can actually get the highest performance, or the minimum delay. And what we'll do is we'll do a little bit of an example where on slide 21, and I'm probably mixing things around a bit and I'm just jumping, but I'll go back. What you'll find is counterintuitively, and this is another important example, counterintuitively you would think I've got one inverter driving you know, a large network which has got 64 units of capacitance, that this is going to be the fastest, right? What you can actually prove it to yourselves is actually, if you work out what the delay is, you can actually see that this one is actually the fastest, which is also the one which ensures that you've got the same logical effort at each stage, right? And because remember, GI is 1, HI is 1 stage, C out on C in, right? So it's 4, 4, 4, right? Anyway, we'll do the calculations in the next few seconds, or the next couple of minutes, but the point is it's counterintuitive, but sometimes adding extra stages actually makes you go faster. And essentially all that's doing, all it's really saying is that you're actually putting more drive in the overall circuit, right? You're able to generate more current in that circuit, but you're doing it in such a way that, hey, I'm filling in this smaller bucket, which then is filling in this other bucket, which is a little bit larger, which is filling in this other larger bucket, and doing it in such a way that it gives me the overall lowest delay. Okay, so the minimum delay is equal to the overall path effort to the 1 on the n number of stages times n plus the parasitic delay. That's the total delay that you get in that path. And why is this result significant? And I'd like you to go through this. Is that it proves that the minimum delay path can estimated knowing only number of stages, the path effort, and the parasitic delay. I don't need to tell you anything about the transistor sizes, right? In order to be able to calculate what the minimum delay is going to be, right? You get that for free, right? Okay, let's continue. And for example, if you had worked out what the logical effort or the path effort is going to be for each of the components, what you can then do is use this to do the sizing of your gates. All right? So this actually tells you, this actual formula actually tells you how to size your gates in order to get the minimum delay. Right? So what it's saying is the minimum delay is C out times GI on FI, and that's your input capacitance. So usually what you need to do is you start from the load, you start going backwards in order to work out how to size each of these gates in order to get the minimum delay. All right, let's do a quick example. Even though I was kind of hoping to go quick today, I seem to get too excited in the how do you call it, what I'm describing, that I take a lot longer. Okay. So let's look at this particular example, and we want to work out the delay from some path A to B, right? And in this particular case, let's make this A to B. All right. And what we do is we go through, look at the tables, and we work out what our logical effort for each of these components is going to be. Remember, some of these have got 3, some of these have got 4 inputs, some of them have got 2 inputs. So you've got to look it up and make sure that you've got the right values. You've got the parasitic delay, you've got the electrical effort, and then you've also got the branching effort. I should have done this. Yep. That's right, for this input. So the branching effort is that. So what you can actually do is you can actually work it out, or or you can actually use this formulae, which is and you can actually work out your G, your B, and your H, and you get 125 units of total delay. Now, suppose I asked you here, for this circuit, how would I size each of these elements so that I get the minimum delay? How would you do it? Okay, so let's look at it, right? So we say that the best stage effort, so we know the parasitic delay, we know that the stage effort is going to be 125. There's 3 stages, so the 1/3. So therefore each stage should have a delay of 5 units. So therefore what we've got is the total delay, which is a sum of FIs, which we've now said is the optimal, right? Because there's 3 stages. F is, we've worked out to be 125. We said there's 3 stages. So now let's work out what the optimal size is going to be. So we can say 125 to the power of 1/3 is going to be 5. So our total delay is the sum of FIs. We said each one's going to be 5. So 3 of them is going to be 15. So the total delay, including the parasitic delay, is 22 units. So that's our minimum delay that we can get through that circuit if we optimally size it. That's what we're trying to do now, is we're trying to optimally size it. Okay? So now let's size the gates. We know that it's C out times GI by on F, and here we've said F is 5. So if we look at this circuit, right, we know the output's 45. How big should Y be? Okay, so let's use the formula. We go 45 units. What's its logical effort? It's because it's a NOR. It's 5 on 3, right? What's our optimal best effort gain? 5. So the size should be 15 units, or 15 units of input capacitance. Okay. Let's now go, let's move back one stage. How should we work out how big should we make X? Well, we know that we've got 2 Y's, and this is why I'm doing this specific example, right? If you only had 1, what would go here? I've got 2. What goes here? 30, right? That's why I'm doing this specific example for you, right? I've actually put a branch in there in order to, not to try to trick you, but to actually point out that depending, that you have to include the total capacitance, right? When you're working out the size. So therefore it's 15 plus 15 because there's 2 Y's in parallel. The GI on the F, so it gives you 10 units. Right, so therefore now you can actually work out what the size of all of these components is going to be. All right, let's do one last example before we got to call it a day, or I've got to call it a day because. All right, let's now look at this very interesting example. All right, and as I've mentioned to you, what we've got here is I've got an inverter driving some kind of circuit. Right, in this particular case, I've said the circuit is, I'm approximating it by 64, how do you call it, a capacitance of 64 units of equivalent capacitance to an inverter. And what I've done next to it is actually put another circuit where I've got 2 buffers, 3 buffers, 4 buffers. And what I'm doing here is working out the total delay, right? The DF in this particular case. And we know that Fi is what? Gi times Hi. What's Hi here in the first case? So input on output capacitance, so it's 64. So 1 times 64 plus the parasitic delay of an inverter is 1. So it's 65 units of delay. Okay. Let's look at circuit number 2. Okay. What's Hi here? 8. And here, again? 8. All right, so therefore we got 1 times 8. And these are times, right? So even though I've got dots, I'm actually meaning multiplication, right? All right, and here we got 64 and 8. Where does the 2 come from? 2 parasitic delays. Okay, so therefore the delay here is 18 units. Okay. Let's do it here. 1, so there's 4, 4, 4, plus 3 units of delay. The total delay is 15 units. So what we're finding is by adding extra inverters, so, you know, this preserves the logic function, but, and what here, I've got extra inverters and they've got much larger size, so they've got larger drive. This circuit's actually the fastest circuit so far. What you can also show is, even if I do 4 and choose it in this particular way, it's not as fast as 3. What you can actually show is, if you use that trick where we're saying, you know, if you've got the total logical effort, what can I work out is to be my optimal number of stages, and what's the logical effort? What you'll actually be able to do is show, for this particular case, it's actually 3 stages, and what you're able to do then is actually work out how to size each of those components, so that you get minimum delay. Right. All right. Everyone excited? Everyone understand this? No? Yes? Why do you care about this? Let me just ask you a different way, other than I might be on the exam, or, you know, Stan's forcing me to learn it. What's the use of it? Yeah, so you can make it so that it's optimal. Yeah, perfect, excellent. And the important things is, it's not necessarily, the smallest number of stages isn't always the best, and that's something that's important, because it's, in many cases, it's counterintuitive. After you've looked at it a few times, you're like, oh yeah, of course, right? You know it's almost like, I've got gears. You can almost think of it like gears on your bike, right? If you had 1 gear, and it might not be the best. Whereas if you had multiple gears, and, you know, using the torque of multiple gears, you can actually get more performance. It's the same thing here. That's all we're just pointing out. That intuitively you might think least number of stages is the best. Actually, that's not necessarily the case. Right? Okay. And there, in the next one, I'm actually just showing you, you know, if we looked at this circuit as an example, if I gave you this circuit, right, and we looked at the overall effort, a path effort, we know that it's 64 units. So therefore, if we wanted to work out what's the optimal number of stages, if we use our formulae, we know that it's 1 on n, so it's 64 on 1 on n. So if we go through and work out n equals 1, 2, 3, 4, we can actually work out what our path delay is, and it'll actually tell us what our optimal path delay is going to be. Right, and then what we can do is, rather than me drawing these for you and actually putting the values in, if I said to you, well, you've got 64 units of of logical effort, what's the minimum delay, and what's the optimal number of stages. You can actually work that out, and then what you can actually do is use the formula where we have worked out, you know, the capacitance, the input capacitance given the output capacitance. You can actually then work out the appropriate size of the gates, and what you can actually see is if you've got something ending in 60, which has 64, you're trying to end something that's driving 64 units of capacitance. The previous stage should have 16 units of capacitance, so therefore the logical effort's 4, CN2's 4, and CN's 1. Okay. That's it for today's lecture and everything on logical delay. All right, so it should be exciting. What we'll do on Friday is we'll start talking about energy consumption and how to minimize energy consumption. All right, I apologize, guys. I really need to go, so I won't be able to answer any questions today. So if you can hold off till how do you call it, Friday, that'll be great. Okay.
When you're like really tired and you come home and you're just really, really happy because your room's clean. I don't know if you get that, especially if you're like really tired and you don't remember cleaning it. It's kind of like that when you come to a lecture hall after somebody else and everything's like all set up and clean. Like, because sometimes you come in, all the boards are all messy and you got to move everything around. But like when it's all done, you're just like, oh wow, I'm like so organized. I'm improving my life. So when you all end up starting to teach, if you end up teaching, this is the experience you'll have. Just like cleaning a room. Kitchens are the other one. I always appreciate it when like I actually pack stuff up the night before. Yeah.